This is a fully functional, custom-designed C64 laptop, built like it could have existed in the 1980s, but powered by modern hardware. Since Commodore never made a laptop version of the C64, I decided to design one and bring it to life. This video shows the full journey from concept to working prototype. So, Commodore's first attempt at a portable computer was the SX64. But technically, it was what's known as a luggable. And while it was groundbreaking for its time, at nearly 22 pounds or 10 kilograms, it really stretched the definition of portable. So I redesigned it as a proper laptop. I took inspiration from the Macintosh Portable and combined it with the design language of the C64. I quickly sketched the idea out on paper, keeping the classic C64 shape, including the vents and the keyboard. The display bezel was inspired by Commodore's old monitors, and right here I added a carry handle that slides back into the case and stays hidden when you don't need it. With the sketch done, I moved on to modeling the concept in 3D. I started with the outer shape, then designed the hinge mechanism that holds the display, the carry handle and the custom keyboard with its own PCB. After that, I added all the internal mounts for the electronic components, along with the design elements that make it instantly recognizable as a C64. With the model ready, I split it into several parts so they fit on my 3D printer. And then finally, it was time to print them. For this project, I ended up with about 30 printed parts. Now it's time to clean them up and remove all the supports. Once those were off, I could start gluing the parts together. Lining up 3D prints isn't always easy, and with superglue setting so fast, you don't get much time to adjust. That's why I add small holes along the split edges for stainless steel dowel pins. They help keep everything aligned and make the joints a lot stronger. With the pins in place, I put some superglue on the edge and pressed the parts together. I repeated the same process for the remaining parts until the whole case started taking shape. Once the glued parts were dry, I started sanding out the print lines with 280 grit sandpaper, then worked my way up to 400. It takes forever, but it'll be worth it. I spray each part with a few coats of primer. It evens out the visible layer lines and gives the paint something to stick to. The next step is gluing the feet onto the bottom part. Now that all the parts are primed, it's time to apply the final color. But before I start spray painting, I need to find colors that are as close to what the original Commodore 64 used. To do that, I'm using my original C64 as a reference and comparing it against this color palette. It helps me find the closest match, and with those values, I can order the right spray cans. The case is complete, so now it's time for the real challenge, the keyboard. I need to print 66 keys for this build. To get a cleaner surface, I swapped the 0.4 nozzle for a 0.2. It takes longer, but the layer lines will be almost invisible. At 0.06 layer height, the whole print will take over 24 hours. After seeing how clean they looked straight off the printer, I decided to skip post-processing and just spray them directly. While the keycaps are drying, I'm going to recreate the layout of the C64 keyboard. I removed all the keys from my Commodore 64 and placed them on a flatbed scanner. Then I used tools like Photoshop and Illustrator to turn that into a clean vector version. Now the big question, how do I get those tiny graphics onto the actual keycaps? I like to use water slide decals. They're super cheap, easy to work with, and perfect for custom designs. But printing white, that was the tricky part. Most home printers just can't do it. White toner cartridges exist, but they're insanely expensive, and of course there wasn't one available for my printer anyway. Then I found white refill toner powder, way cheaper and compatible with my printer. So I took an empty black cartridge, cleaned it out completely, and filled it with the white powder. And just like that, I was finally able to print in white. To make my life easier, I bought this used Silhouette Cameo 1 for just 50 bucks. That way I don't have to cut out each character by hand anymore. It's an older model, but it still works great. It cuts the predefined areas cleanly, saves me a ton of time, and the results look way better than cutting each by hand. I lined up all the keys on a piece of cardboard. Then I applied the water slide decals. Like the name says, you dip the decal into water for a few seconds, place it on the key, and slide the print onto the surface. While it's still wet, you can shift it around and line it up exactly where you want. By pressing it down with a dry paper towel, you can fix it in place permanently. It took me 3 hours to complete the whole keyboard, but seeing it come together made every minute worth it. With all the decals applied and dry, the last step is sealing them in. I'm using clear coat not just to protect the print, but to smooth out the edges of the water slide film and make the keys look more uniform. After a couple of coats, the edges pretty much disappear. Alright, keycaps are done, now I can finally get to the keyboard PCB. I had it manufactured by PCBWay, who is also the sponsor of this video. They made this board, along with a few others for the project, and everything came out exactly how I designed it. Big thanks to PCBWay for supporting this project. They also offer 3D printing, CNC machining, and a bunch of other cool services for makers. So if you're working on your own project or just want to see what's possible, check out PCBWay.com. For each key I need to solder a diode. It prevents ghosting and makes sure only the correct keys get registered. Soldering over 60 of these isn't the most exciting part, but it's necessary when you're building a custom keyboard. This is where I'll be installing a Raspberry Pi Pico. It runs the QMK firmware and works great for this layout thanks to its many GPIO pins. I'm using pin headers instead of soldering it directly in case I ever need to swap it out. To mount the key switches, I 3D printed this key switch plate. I will use these white MX switches left over from a prototype product I designed for a client, and I will probably never need them again, otherwise I would have gone with black ones. With all the key switches in place, I aligned the PCB on the back of the key switch plate and then I screwed the two parts together. Now I can solder the switches to the PCB. Fortunately, it's easier than soldering the diodes. But after building one keyboard, you're pretty much cured of wanting to build another anytime soon. For shift lock, I'm using a mechanical lock switch, just like the original C64. Most modern keyboards do this in software, but I wanted that proper mechanical feel. Turns out I installed a regular switch by mistake. I swapped it out for the lock switch and soldered it to the PCB. With the Pico installed, it's time for the keycaps. After all the work, it's great to see everything taking shape. The last step is installing a stabilizer for the spacebar. It keeps the key from wobbling and makes sure it feels smooth when pressed off-center. And with that, the keyboard's finally done. Now let's take a look at the bottom shell. These holes are for threaded brass inserts. They make the connection stronger than just screwing directly into the case. I pressed them with a soldering iron so they melt into the plastic and stay firmly in place. For the hinge mounts where the display will be attached, I'm inserting regular hex nuts into the recessed slots. They fit tight, but just to be sure they don't fall out, I'm adding a small drop of superglue around them. Then there's the carrying handle, and as I already mentioned in my sketch, I wanted something a bit more interesting here. I'm using a push latch like the ones you usually find in closet doors. Press once to hide the handle, press again and it pops out. It's simple, inexpensive and a really elegant solution. I could have designed my own mechanism, but sometimes there's no need to reinvent the wheel, especially when building prototypes. Now I'm attaching the magnet to the handle and placing it into the case where it connects to the push latch mechanism. The handle can't just sit loose inside, so I 3D printed a plate that fits right above it. That keeps it in place and also adds supports for the components that will be mounted on top later. I also want to be able to connect old joysticks, the ones that use the classic 9-pin connector, just like the C64 had. Here's the board I designed for it. I'm adding 2 9-pin connectors and a power switch in the same style as the original, just with slightly different dimensions. I also 3D printed the cover plate, and when placing it on the board, you can really see that the metal connectors don't match the look. The original C64 used black plastic ones, and finding those today isn't easy. Some sellers ask around $15 for just 2 of them. The metal ones on the other hand cost less than $4 for a pack of 10. So I decided to modify those instead. I removed the metal covers, 3D printed black replacements and glued them on. The result looks almost identical to the originals. Now I can solder everything to the board. The modified connectors, the power switch, 2 pin headers that connect the joystick ports to the computer, and a terminal block for the main power input. To finish it off, I used water slide decals on the cover plate to match the printed text from the original. The plate slides neatly into the case, and right behind it goes the board with the joystick ports and power switch. It all lights up just as planned, which is always a relief when you've been modeling parts for hours on a screen. Then I attach a cable with a JST connector. This one will later connect the power switch to the battery controller board. Then I plug in the cables I made for both pin headers. They connect to the computer I'll be using. This 3D printed plate is where most of the internal components will be mounted to. And as you can see, I've already added the brass inserts. A few screws later and it's secured to the bottom shell. The first component I'm mounting on the plate is the USB hub. It's attached to a small 3D printed bracket with screw holes, and I replaced its USB port with a cable. The SD card slots and USB ports make it easy to load programs and games from flash drives or connect USB joysticks. And this is what drives the whole thing, a Raspberry Pi 5 that will run the Vice emulator. It's affordable, powerful, and with an NVMe drive it boots slightly faster. I mounted a heatsink with a temperature controlled fan, so it only turns on when it's needed. The Raspberry Pi is secured with brass spacers, and on top of those I'm mounting the PCB that holds the M.2 SSD. One thing I really wanted for this build was the ability to use original Commodore peripherals, like the 1541 floppy drive or the dataset. But how do you get that old hardware to work with an emulator on a modern system? The cool thing is, with the OpenCBM library and a custom-made adapter, you can actually use these old floppy drives directly with the Vice emulator, which already has a built-in support for OpenCBM. That was the easiest part. But as far as I know, there isn't any solution that connects the original dataset directly to Vice, at least not in the same seamless way. After some research, I came across this open source project called TapeBuddy64. It's an adapter that lets people back up their old tapes into a digital format called .tap. With that file you can either make a new copy to an empty tape or load it straight into an emulator. I figured this could be a great starting point for making my own adapter, one that loads tapes directly into Vice when you press play, just like on the original machine. I tried sourcing all the parts, but the delivery times for some of them were quite long, especially for the main chip. So instead, I ported the source code over to an Arduino Pro Micro, which you can find almost everywhere. I etched a homemade connector that plugs directly into the dataset and modified the client software to communicate with my adapter. After a few days of tinkering with the firmware, I finally managed to get usable data from it. The only thing I couldn't solve yet was how to make the experience seamless without having to manually load the tab file into Vice every time. I didn't have a solution at this point, but I had an idea that might fix it, which I will get back to later. For now, I redesigned my homemade adapters into proper PCBs, soldered everything together and installed them on the plate. This holder is for an HDMI extension cable. It forwards one of the 2 HDMI ports from the Raspberry Pi to the back of the case. Next to it goes an Ethernet breakout board, which is also just an extension of the port on the Raspberry Pi. Then there's this empty slot here. My initial idea was to add a cartridge reader, but since cartridges weren't really common in Europe back then, it's even harder to find any nowadays. So I decided to leave the space closed off with a cover, using 2 strips of double-sided tape. I might get back to it if I get my hands on some cartridges, or maybe I'll put something else there instead. If you've got an idea what that could be, let me know in the comments. This DC power socket will be the 12V input that powers the whole thing and charges the battery. I soldered a cable to it with a JST connector and mounted it on a small 3D printed holder that will be attached to the back of the case. To power the Raspberry Pi, I'm using a buck converter that brings the voltage down to 5V. I still need to adjust the output voltage, but I'll do that once the battery board is installed. I wanted an easy way to adjust the screen brightness and volume, so I made a front plate that fits into the opening on the left side of the case and fixed it in place with 2 drops of super glue. Then I mounted 2 potentiometers into this holder, one for brightness and one for volume. I pressed 3D printed knobs onto the shafts, and once everything lined up, the whole assembly was fixed in place behind the front plate, ready to be connected to the circuit. For the battery, I'm using something off the shelf. I found this uninterruptible power supply, or UPS, for about $10. It didn't come with any batteries, but it has everything else I need built in. Inside, there's a PCB with 6 slots for 18650 cells, and it handles charging, balancing and voltage conversion. On the back there are several output options. A USB port that provides 5V, but it's not reliable enough to power the Pi. For that, I'm using the 9V output, which will power the Pi through the buck converter I installed earlier. Next to it is a 12V output, which I'll use to power the screen. The 12V input gets wired to the DC barrel jack on the back, and the power switch gets replaced with a cable that runs to the one on the joystick board. There are also 4 small LEDs on the top that show the battery's charging status. But after the board is mounted inside the case, those LEDs won't be visible anymore. So I want a way to monitor the battery status on screen and somewhere on the case. The plan is to make a small Python program, basically an overlay that sits on top of the Vice emulator and shows the battery icon with the current charging state. To do that, I'll need to modify the PCB slightly, so I can forward the state of each LED to the Pi. Whenever one of the LEDs turns on, it triggers an optocoupler, which then activates a GPIO pin on the Raspberry Pi and tells the Python program what to display. The optocouplers keep the circuit safely isolated, so I don't accidentally send voltage where it shouldn't go and let out the magic smoke. First, I removed the surface mount LEDs and their resistors. I'll be using different resistor values anyway, so I bridge over the original pads and soldered cables where the LEDs used to be. Next, I desoldered all the output ports and replaced them with JST cables. Each one will be labeled with its voltage to keep things organized. The circuit with the optocouplers will go on the perf board and connect to the battery board using the cables I soldered to the LED pads. Since there's plenty of space for more components, I'm going to mount an audio amplifier here as well. It's a small module that will later power an internal speaker. It has a stereo potentiometer soldered on by default, but I'm replacing it with a socket that connects to the volume knob I mounted earlier. Now that the circuit is ready, I can start installing everything into the case. This part holds the battery controller board. I designed it to fit right into the opening on the bottom, so I can easily access the battery cells from the back. After another round of super glue, I can press it into place. Then I push the charge indicator LEDs into their slots. Once that's in, I place the PCB on top and secure it with 2 brackets and a couple of screws. Then I install the perf board, hook it up to the battery PCB and connect the volume potentiometer to the amplifier. After connecting the power lines from the battery, I plug in the 12V power supply and use a multimeter to adjust the buck converter down to 5V. Once that's dialed in, I start plugging in some components to the Pi and its GPIO pins. If you're wondering why nothing's mounted to the standoffs, I was thinking about adding USB hub modules. But with the current setup, the 4 USB ports on the Pi are enough. The ones next to it could be used for another perf board or maybe a mount for a future cartridge reader. Now let's get to the final hardware part of the build, the screen. I'm using a 10-inch 4x3 panel which comes with a driver board and an inverter for the backlight. But there are a couple of things I want to change. As soon as the screen turns on, it shows these annoying message boxes, like a no signal warning or an HDMI pop-up, and there's no option in the menu to turn them off. The other thing is brightness control. In order to make it work with the brightness knob I installed earlier, I need to do a small mod on the inverter. On the back, there's a pin labeled ADJ, short for adjust. The driver board controls brightness by changing the voltage on that line. So I cut the cable going to the ADJ pin and add a potentiometer in between. Now turning the knob, adjust the screen brightness. And to get rid of those pop-ups, I need to modify the firmware on the controller board. I'm using a USB flash programmer and an SOIC clip to dump the firmware from the chip onto my computer. The method I'm showing works with controller boards that use the Realtek RTD2660 chip. Luckily, some smart people have already reverse engineered the firmware and made the tools and documentation available. You can either open the firmware in a hex editor and change a few values manually, or use this flash tool by Flops, a simple application that lets you modify the firmware with just a few clicks. Then I flash the modified version back onto the chip, and the result is exactly what I was aiming for. The pop-ups are gone and the screen goes straight to the desktop. Before I can mount the display into the top cover, I need to press in a few more brass inserts. Around the case and the bezel are slots for neodymium magnets. They are strong enough that the bezel locks in place without screws and is easy to remove for maintenance. After that, I start mounting the display electronics. This cable is soldered to the audio output on the controller board and connects to the amplifier. Then I install the inverter board, where I also solder the cable that connects to the brightness knob. And finally, I mount the screen panel with 4 screws. Now I can connect the HDMI cable that runs to the Raspberry Pi and a power cable that goes to the 12-volt output of the battery. This half-round cover snaps into the gap in the hinge area. Its main job is to hide the cables and keep them in place when I open or close the lid. And to lock the lid, I added 2 sliding hook mechanisms, one on each side. Each has a spring that snaps it back into place after unlocking, so the lid stays securely closed. Now that the display unit is assembled, I can move on to the hinges. If I mounted them like this, the screen would just drop down and never stay in place. To fix that, I'm using these small torque hinges. They add just enough resistance when opening the lid, so the screen holds its angle without falling down. Next, I drop the display into its slots in the main case and secure the hinges with 8 screws. And for the first time, it starts to look like a laptop. The internal speaker gets mounted to the top cover and is fixed in place using UV glue. And lastly, I'm attaching the keyboard using 12 screws. Now with the keyboard mounted, it really starts to look familiar. These are original Commodore 64 badges, and they fit perfectly into the recessed areas. It's definitely tempting to just glue them in and call it a day, but they're actually borrowed from someone who is in the middle of restoring a C64, so I should probably give them back. Besides, using the originals just wouldn't feel right, at least not without real Commodore hardware inside. So for this build, I'm making my own. I 3D printed this one using a 0.2mm nozzle and spray painted it with the same color I used for the F keys. Then I cut the outline of the debossed lettering from metallic vinyl and carefully placed each piece on top. I sealed them with clear coat and added a strip of double-sided tape on the back. I start by inserting the power badge, followed by a 3D printed holder for the power LED. Then I slide a plastic ring onto the LED cable, insert the LED into the holder and lock it in place by pushing the ring onto the back, just like it was done on the Commodore 64. Now I just plug in the speaker and the keyboard, and with that I can finally finish assembling the laptop. And with that, the portable 64 is finally done. Let's switch it on and see if everything works the way I imagined. Now, it might look fast in the video, but in reality it takes about 11 seconds to boot. The key switches sound really satisfying, and I couldn't be happier with how it feels to type on this thing. For the first test, I'm typing in the command for the classic random maze program. Alright, that looks good. Next up, I'm loading a game from the 1541 floppy drive. When I bought my Commodore 64, it came with a few boxes of floppy disks, and in one of them I found this 40-year-old copy of Pac-Man. Let's hope it's still readable after all these years. And it still works. Now obviously you don't want to play this without the proper controller. So I plug in the Competition Pro joystick into the 9-pin port on the side and start the game. A Python program running in the background converts the joystick inputs from the GPIO port into key presses. Now let's test if it loads directly from the dataset. On a real C64, when you enter the load command and hit play on the dataset, it should start reading from the tape right away. Which I didn't get to work before, but now it's finally working. To make that happen, I modified the client software that communicates with the dataset. When the Pi starts up, it automatically launches the client, which creates a blank tab file in the Linux temp folder. At the same time, it connects the Device Emulator's remote monitor using Telnet and attaches the tab file in the background. Then, when you press play on the dataset, it streams the signal in real time straight into the tab file, basically feeding a live tape into the emulator. It even forwards the send signal, so pressing stop or play on the actual dataset controls the virtual one inside Vice. It's a bit of a hacky setup, but it works perfectly for this prototype. 10 minutes of tape loading later and I'm in the game. It still amazes me how much joy these simple games can bring, even after 40 years. And of course, with 2 joystick ports, you can go multiplayer. For me, being able to connect this original hardware to my portable 64 is pretty awesome. But let's be honest, carrying all this extra gear isn't exactly convenient. They are bulky, the floppy drive needs external power, and you'd need to bring a bunch of tapes and discs with you. And that's why I use this, an SD card loaded with a bunch of games. The kind of floppy they could only dream about in the 80s. And it's super easy to use. You just insert it, press the logo key in F7, and a Python-based overlay pops up. Scroll with the arrow keys, select the title, hit enter. It loads the D64 file straight into Drive 9 using the remote monitor in the background. Type the load command and you're ready to play. And since the portable 64 has a built-in handle on the back, I just push it and it slides out. Now I can carry it around like a C64 briefcase and take it pretty much anywhere. With its 4 kilos or about 8 pounds, it's actually pretty easy to carry. That gives me the option to play some classic games in the park, write some basic code in the coffee shop, or even bring it to the beach. Because that's what normal people do, obviously. This took a few months, a lot of super glue, and most of my sanity. I worked on this every spare minute I could find, and honestly, I enjoyed every second of it. Hope you enjoyed following along, and maybe it even sparked some ideas of your own. If you want to see more unnecessarily complicated builds like this, you know which button to press. Thanks for watching, and see you in the next one.